Good morning, my name is Moya and I'm from the Bacterial Infections and Antimicrobial Therapies group, and I will be presenting my work titled A Clearing Protocol for Galleria melonella larva Visualization of Internalized Fluorescent Nanoparticles. A bit of background: Galleria melonella is an animal model that's used to study pathogenic infections, toxicity of compounds, among other things. It's gaining popularity as a model because it can be used as an alternative non-rodent in vivo model, so we can potentially reduce the number of rodents used for various studies. Optimal clearing would provide new insights on larva visualization, which can greatly benefit further applications. Before clearing, we have a larva that has a thick cuticle and it's not transparent, so there's strong scattering of light. If we do clearing, we would end up with a larva that is transparent. It has a high RI, or refraction index, so the light can penetrate with minimal scattering. So the aim of this study was to optimize a clearing protocol in Galleria melonella larva using fluorescent rhodamine nanoparticles as proof of concept. For protocol optimization, we tried different approaches which focused on three main steps: fixation, permeabilization, and clearing. For one of the approaches was to first dehydrate the larva in either ethanol or methanol in increasing concentrations and for different incubation times. And then the other approach in the bottom part of the screen was to do detergent followed by increasing concentrations of sucrose, or either placing the larva at a highly concentrated solution of sucrose. By seeing the images of the larva, we can say that only this protocol was the one that achieved successful clearance. So our final optimized protocol was to first inject the larva with red fluorescent nanoparticles, followed by overnight fixation in paraformaldehyde, and then the larva would be dehydrated in increasing concentrations of methanol, and then we added an extra step where we did a 1-to-1 ratio of 100% methanol and the clearing solution. The clearing was done with 100% BABB, or benzyl alcohol plus benzyl benzoate, 1-to-2 ratio, for at least 7 to 10 days. Once the larvae were cleared, we tried to image the larva under a confocal microscope to see if we can detect the nanoparticles inside the larva. Here in figure A, we can see a non-cleared larva with nanoparticles, and we can't detect the nanoparticles as the laser cannot penetrate the thick cuticle. But if in B, we can see a clear larva injected with PBS, and the laser can penetrate very deep, up to 187 micrometers. C and D images are clear larvae injected with nanoparticles, and we can see the red nanoparticles deep inside the larva, up to almost 220 micrometers. We also tried to measure the relative fluorescence emitted off of the nanoparticles in cleared and non-cleared larvae, and compared against negative controls. In this graph, we have the values represented by induction factor. In non-clear larvae, the values are more or less the same, but in clear larvae without nanoparticles, we see an increase, which is due to the intrinsic autofluorescence of the larva, that we can detect it better. And then with nanoparticles, we see an induction factor of almost 13, which is we can successfully detect the nanoparticles inside the larva. So conclusions: a tissue clearance protocol has been obtained for the first time in Galleria melonella larva. Internalized fluorescent nanoparticles could only be observed with confocal microscopy in cleared larvae. Relative fluorescence of internalized nanoparticles was only measured in cleared larvae, and this approach can contribute to the study of nanoparticle interactions within living organisms. Thank you for your attention.